Have you ever looked at a massive app on your phone and just wondered, how in the world does this thing not collapse into a giant, messy heap? Well, the secret? It's the blueprint. Today, we are diving into system design, which is basically the architectural plan that engineers create before a single line of code ever gets written. And that right there, that's the fundamental challenge, isn't it? It's not just about getting an app to work for you and a few friends. It's about making sure it can handle thousands, maybe even millions of users down the road. This is where good system design isn't just a nice to have. It's absolutely everything. All right, so what exactly is this blueprint we keep talking about? Let's break down what the discipline of system design really is and what it involves. Now, I want you to really focus on that word strategic. This isn't about the little stuff, like what to name a variable or which sorting algorithm to use. Nope. These are the huge foundational decisions that shape the entire project. They determine how all the major pieces are going to fit together and talk to each other. When you boil it all down, it really comes down to these three core pillars. First up, what's the overall structure? That's your architecture. Then, how are you going to store and handle all your information? That's your data approach. And finally, how does the program actually flow and respond to things? That's what we call external control. And don't worry, we're going to tackle each one. Let's kick things off with the big one, architecture. This is like the 30,000-foot view of your entire system. It defines all the major parts and, this is crucial, how they're all going to communicate. There are a few common patterns or styles that you can choose from. Okay, first up, we've got the pipes and filter model. The easiest way to think about this one is like an assembly line, but for data. So data comes in one end, flows through the pipe, and at each stop, a filter does something specific to it. The key thing here is that each filter is totally independent. It just does its one job. A perfect real-world example is a compiler. It takes your source code, runs it through one filter to analyze the words, then another to check the grammar, then another to generate the final code. It's a pipeline, one step after another. All right, next is a model that you use literally every single day, probably without even thinking about it. Client-server. This is the backbone of the entire modern web. It's a really simple but super powerful relationship. Your web browser, that's the client. It sends a request out into the internet. A web server gets that request, processes it, and sends back a reply, the web page you wanted to see. That simple request and reply conversation is happening billions of times a second, all over the world. But what happens if you get rid of that central server? What if every single component isn't equal? Well, that brings us to the peer-to-peer or P2P architecture. And this is where it gets really interesting. In a peer-to-peer network, every single participant, or peer, is both a client and a server. It can ask for information, and it can provide information. This makes the whole network incredibly resilient. If one peer goes offline, the system just keeps on chugging along. You've seen this in action with apps like BitTorrent or even the original version of Skype. And for our last pattern, let's look at a really dynamic model that's all about events, the publish-subscribe pattern. You might also hear this called pub/sub. Think about your social media feed. When someone you follow posts a new picture, they are publishing an event. You, because you subscribe to their feed, get a notification about it. The really cool part is the components don't need to know anything about each other directly. They just care about the events. This makes the system super flexible and easy to scale up. Okay, so we've looked at the overall structure, the architecture. Now let's move on to the next two critical pieces of the puzzle, how we're going to handle our data and how we're going to manage the program's flow. When it comes to data, you've got a classic choice. On one hand, you have a formal database. These are powerful, they're great for lots of users at once, but they also add a lot of complexity and overhead. On the other hand, you've got simple, flat files. Think of a basic text file or a spreadsheet. They're super easy to set up and use, but they lack all the fancy features like letting multiple people make changes at once. It's a trade-off. And how does your program actually, run? Well, a procedure-driven program is like reading a book. It starts at page 1 and follows a very specific, predefined path to the end. But an event-driven program, that's more like a choose-your-own-adventure book. It just sits there and waits for an event, like you clicking a button or typing something, and then it reacts. Most modern graphical apps work this way. So we've got our architecture, our data plan, and our control flow, but what actually separates a good design from a bad one? Well, it turns out there are two guiding principles that are absolutely essential for creating a clean, strong, and maintainable blueprint. You can really think of these two ideas as the yin and yang of software design. They're in this constant, delicate balance. Cohesion is all about what's happening inside a single piece of your software, a single module. And coupling is all about how those different modules are connected and talk to each other. So your goal is always high cohesion. You want every module to be an expert at just one thing. For example, a dice module should handle everything related to dice, rolling them, showing the results, whatever. It shouldn't also be in charge of drawing the game board. When modules are this focused, the code is just way easier to understand, fix, and even reuse later. And at the same time, you always want low coupling. Think of it like this. Good software is built with Legos, not with superglue. Lego bricks connect in clean, predictable ways. You don't want your software modules to be a tangled mess of wires, all dependent on each other. When coupling is low, you can change one piece without causing a catastrophic chain reaction that breaks everything else. Okay, so after all these decisions and principles and patterns, why does this all matter so much? Why go through all this trouble up front? Why not just start coding? This quote really just says it all, doesn't it? The choices you make way back in the system design phase have this massive ripple effect that carries through the entire life of the project. A bad architectural decision you make on day one can cause gigantic headaches and cost a fortune to fix years down the line. At the end of the day, a good blueprint is an investment. It pays off by giving you software that isn't just reliable and easy to maintain, but is actually built with the future in mind. It's how you build systems that can last, that can evolve, and that ultimately are successful. So I want to leave you with a little challenge. The next time you open up your favorite app, Spotify, Instagram, whatever it is, just take a second, pause, and think about how it might be working under the hood. Can you guess its blueprint? Is it a client server talking to a massive database? Does it use pub/sub for notifications? Because once you start seeing the blueprints, you'll never look at software the same way again.